Thank you for listening to this presentation on optimism, enabling collaborative implementation of domain-specific metaheuristic optimization. My name is Megan Hofmann, and I'm an assistant professor at Northeastern University, and I present this work on behalf of my many co-authors. The goal of this work is to help us build domain-specific tools that require the expertise of both domain and technical experts, that is, programmers who can implement these optimization tools. And we do this to support a variety of different domains of generative design and fabrication, such as machine knitting, the creation of tactile graphics for people who are blind or have low vision, and the creation of medical devices such as splints. We do this by leveraging the expertise of crafts communities, people with disabilities, and clinicians and professional caregivers. At the core of optimism is an optimization process for generative design, where a user defines a set of domain-specific goals and objectives, inputs them into a black box optimization process, and gets an automatically generated result. This has been successful in a variety of different domains, such as creating electromechanical devices, creating metamaterial mechanisms, and personalized casts. All of these systems rely on a same basic iterative optimization technique, where the user inputs some initial set of designs that don't yet meet their goals, and then those designs are evaluated based on an objective function. The system will then choose a design and consider whether or not it wants to accept that design. If it doesn't, it will modify it, hopefully to increase its value, and then evaluate the new design. This process is repeated over and over again until eventually a design is created that was acceptable to the end user. The core contribution of the Optimization Programming Toolkit integrating metaheuristic intuitive search methods, or OPTIMISM, are the breakdown of these iterative structures into two different libraries. One is a general-purpose domain-agnostic library provided with Optimism, and one is a domain-specific library that is created by programmers and domain experts. First, the library of domain-specific designs creates a customizable objective function. And then, using domain-agnostic strategies, we select a design based on the objective scores. Using another domain-agnostic strategy, we decide whether or not to stop this process using stopping criteria. And then finally, we break down the modification step into two different components. First, we select a modification, and next we apply that modification. The strategies for selecting modifications are domain-agnostic, and the application of those modifications is domain-specific. A key feature of optimism is that the domain expert and the programmer must build a domain-specific library in order to enable these tools. They do this by creating different heuristics, which consist of objectives and modifiers. An objective expresses the design goals of the end users. Objectives are functions that, given a design, will return a value between 0 and 1, where 1 is performing well on that goal. Modifiers make small changes to designs. A modifier function takes in a design and produces a slightly different design, hopefully meeting one of those objectives. Objectives and modifiers plug into different components in the iterative process, in the evaluation and modification stage. Given the concept of objectives and modifiers, we can then construct what we call heuristic maps. First, we rank different objectives using different values to assess their significance to a problem. We then apply different modifiers and provide heuristic weights between each objective and modifier. A high weight between an objective modifier expresses that a modifier is very effective at improving a specific objective. Once a programmer and domain expert have built out these different objectives and modifiers, the heuristic maps can be configured by end users in an automatically generated user interface. Once we have heuristics, we still want to create a strategy that is domain agnostic and can generalize to a variety of complex domains. To do this, we focus on metaheuristic optimization. Consider first hill climbing methods that would apply these best heuristic at each given point over and over again. While these can be effective in some domains, they tend to produce results that are going to be near local minima and not close to global minima or the target designs desired by users. Metaheuristic optimization uses a meta strategy to apply heuristics when searching for high-quality criteria, and this enables it to meet multiple objectives. Kind of like heuristics are related to objectives and modifiers, we can deconstruct metaheuristics into design and modifier selectors. Design selectors are functions that choose an existing design based on the scores in the objective function, and modifier selectors choose a modifier from the heuristic map to apply to the selected design. That is, they go into the design selection and modification stages in the optimization system. Consider again how we can use heuristic maps to create modification and design selection strategies. We can use the scores of the objective functions to evaluate how effectively different designs are meeting the final criteria. So for example, we could select something such as a random design, or we could select the best design, and we can control between these two different states using an entropy value. Alternatively, we can use heuristic weights to determine which modifiers are best to select at any given time. We do this by building on prior work that evaluates the expected improvement of each modifier given the current objective scores. Again, we can think of modifier selectors as ranging between selecting a modifier randomly and also choosing the best expected modifier given the current system. By mixing and matching different design selectors and modifier selectors, we're able to emulate many different optimization techniques such as simulated annealing, ant colony optimization, taboo search, Monte Carlo Markov chains, variable neighborhood search, and many more. We evaluate this work through a series of demonstrative generative design tools on automatic patient-specific cataract lens selection, hand-split fit optimization for bioccupational therapists, and tactile graphic and map optimization for blind users. We're going to only talk about these three areas as they're specific to some of our prior work on focusing on medical making and assistive technology development. First, consider the case of ophthalmologists generating cataract lens selections. We developed this system using an ophthalmologist and a programmer who had never before built an optimization tool. We then asked the two to work together to develop a set of objectives and modifiers in this domain. For example, the ophthalmologist had objectives such as preventing farsightedness in the final results, accommodating for their surgical error, matching to a preferred prescription by the end user, and preventing nearsightedness. They then defined a variety of modifiers, such as decreasing the A constant of their cataract lens, switching the lens model out for different brands, and increasing the A constant. We were then able to take this mapping of the heuristics based on the objectives and modifiers and build an optimization tool with 100% accuracy across 10 prior cases from this ophthalmologist. It had 80% accuracy on selecting the interocular length, and all optimized lenses were determined to be reasonable for clinical use. That is, there might be slight differences in the different selections based off of which doctor had approached the patient. We developed a similar study based off of our prior work working with occupational therapists and their domain expertise. In this case, the occupational therapists are domain experts in hand splinting techniques and already use parameterized designs and tune those parameters to fit the designs to specific people. They considered, for example, many objectives such as thumb flexibility, wrist flexibility, breathability, and fit to the user. Thumb flexibility was determined by parameters along the length of the splint, while wrist flexibility affected the width. Breathability was determined by how many holes were placed into the middle of the splinting material, and all of these affected fit to the user. The optimized thumb splints can effectively attach to many different people's bodies and accommodate their different hand sizes. And then finally, we have conducted prior work on people with disabilities, specifically people who are blind and low vision, and treated them as the experts, identifying specific objectives that are important to their preferences for how information is displayed to them, and modifiers that affect how that information will be displayed based on their varying criteria. We conducted a study with blind and low vision users, and the optimized maps outperformed both standardized tactile maps and customized maps that were generated entirely by the end users. So it shows both the benefits of optimization and customization in this context. Across a variety of domains that we worked on, optimism supports these diverse domains and is able to handle a variety of different models, such as 3D models of parameterized splints, more complex models for tactile graphics, as well as knitted designs that are represented as node link graphs. The main takeaway of this work is it enables an expert-driven optimization, which increases access to domain-specific design tools. Thank you for listening to this talk, and thank you to our many supporting institutions and funders.